I'm Vic Law from HKUST, the Department of Physics, and I'm also representing the Hong Kong Young Academy of Sciences to give this talk. The topic today is on the emergent quantum technologies. So I will talk about this with my co-speaker today, Professor Johnny Ho. So Johnny will talk about other applications of quantum mechanics, other important applications. So I should probably go to my PowerPoint. Okay, so this is the second lecture on a series. This is the second lecture for a series of talks on emerging technologies of our time. So the first talk was on gene editing. Maybe some of you know and attended that talk. And this is the second one on quantum technologies. And we will have more coming, which, for example, on AI and robotics, on science of climate change, on the computer-assisted drug design and topics, and cosmology, so topics like that. So but this is the second talk. So, and today, I would like to talk about quantum computation. And Johnny will talk about other applications of quantum mechanics. So what's quantum computation? And well, first of all, we need a quantum computer. And this is an artistic design of a quantum computer that people can imagine. But fortunately, we are far beyond the stage of just imagining. Actually, people are building quantum computers. And this is a quantum computing chip built by Google. It's called Google's XMON quantum computing chip. And here you see crosses. Each cross represents a bit, a quantum bit. So which I will tell you more about this quantum bit fabricated by Google. Each cross is made by a superconductor. So, and you can use that to do some computation. And also other companies like IBM and Intel, they are also working on quantum computer. So it has been a very hot topic lately. That's why we want to introduce this to our teachers and to our young people. So, and prepare our young people for the opportunities and challenges to come. And this is one of the main purposes of our lecture series, which is to prepare our young people for the upcoming new technologies. So this is the outline of the talk. So I will, before you know about quantum computation, you probably need to know something about quantum mechanics. And where is it from? Why is it important? And what are the main principles of quantum mechanics? Why is it so special? And so first of all, we'll talk about, well, before we have quantum mechanics, how we look at this world. And then I talk about some strange properties of the quantum world. So there are some very strange things about it. And how, in the past almost 100 years after the formulation of quantum mechanics, how it has changed our world. And maybe it will change furthermore in the coming decades. And then I will talk about the power of quantum computation, and then report to you the current progress of quantum computation, and also mention something about that, what I'm doing, which is related to Microsoft's scheme of building the so-called topological quantum computer. So, and before we have quantum mechanics, we had Newton. So the world was described by Newtonian mechanics before we know quantum mechanics. So, and for example, the motions of the objects are governed by Newton's laws, such as F equals to ma that all of you are familiar with. So this really described the circular motion of the Earth around the Sun, the spinning motion of the Earth, and projectile motion of the tennis ball and things like that. So it works very well, even for today. And then, about 200 years later, so we have Maxwell, who really did a very important work. So he formulated the theory of electromagnetism. So he described the electromagnetic phenomena by 4 equations. These equations tells us that, for example, we can explain how light can propagate from the sun to the earth. So, and that's the topic of optics. And they can also explain how magnetic field can be generated by moving charges, such as when you have a solenoid, you pass through a current, and that solenoid will create a magnetic field. So I think you also learned this, and that tells you how to make an electromagnet. And then you have the Maxwell equation also tells you how changing magnetic field can generate electric field. So if you can generate a changing magnetic field, you can actually generate electricity. So that gave you the guiding principles of building generators and generate electricity. So this happened in the middle of the 19th century. So, and starting from the 1970s, actually people know how to use electricity. So that really transformed, that is the beginning of the so-called second industrial revolution. So the second industrial revolution started from about 1870s until 1914. That's the time that the First World War broke out. So, and there was a really golden period of time that people, they know how to use electricity. They know how to use, instead of coal, they use petroleum. Instead of iron, people started making steel. So there was a lot of technological advancements during that period of time. And people's life looks really not bad. They even have television in the 90s, 1920s. After the second industrial revolution, they have refrigerators. You have a lot of cars, even fancy cars like Mercedes. And you have, plenty of lights in your house. You have telephone. Boeing started making airplane start from the 1910. And you have IBM. This is a poster advertisement of International Business Machine. That's IBM. So these companies, these big companies, for example, the company making telephones, it's AT&T, all these big companies, they were actually technological giants at that time, of their time. So, and they still are until today. So that really tells you how important technologies are. If you have technology, you can really do a lot of things. And so life looks good in the 1920s. As I mentioned, you have really good cars. You have AT&T making telephones. You have General Electric, like companies like that, generating electricity. You have airplanes, and you have IBM making all sorts of machines. But against this background, life seems quite good, just like today. We are probably quite happy with the life that we have. But at that time, there was a group of people, they are called physicists. They were studying some problems which are quite seemingly irrelevant to the life of people. And they were asking questions like that. Why atoms are stable? Right? Simply there's nothing to do with your daily life. People, they were asking, why atoms are stable, I have an electron surrounding a proton, but from Maxwell's theory, it tells you that this electron, because when it's circulating around the proton, it is actually accelerating toward the center. You know that accelerating charge from Maxwell's theory tells you that it will radiate. So it will lose energy. That means that Maxwell's theory tells you this atom will lose energy and gradually collapse into this proton and just combine with this proton. And but that didn't happen. Why? Why atoms like that are stable at all? So physicists are asking questions like this. And they also ask, when I look at the spectrum of the sun, for different frequency of this electromagnetic wave, you actually see different intensity, like that. So this is intensity, this y-axis. The x-axis is wavelength. If you look at the sun, and you look at the wavelength, this peak, this roughly is the temperature of the sun. And this is several hundred nanometers. So do you know where this peak is? It corresponds to light of visible light, right? So that's why actually, the sun has this when it emits light, but different light it emits, it has different intensity. So our eyes are adjusted to the intensity where the sun emits the strongest, the light with the highest intensity. So, but actually when you observe this, you realize that, classically, it will give you this curve instead of this one. So again, Maxwell's theory cannot explain this observation. So physicists, they really try to understand some seemingly not very important things, but, they try to understand it. And to explain this kind of phenomena, you need a microscopic theory. You need a theory to describe microscopic objects, such as electrons. And that theory is quantum mechanics. So it took people almost 3 decades to fully understand, to formulate quantum mechanics. And this is a very counterintuitive theory. And this is a very famous picture. And the people here, I'm sure you know many of them, like Einstein sitting in the middle, of course. And behind him was Schrödinger. And then you have a Heisenberg, you have Planck. These are the fathers. And many, many others, like Dirac, Neil Bohr, de Broglie, there are many, many. Pauli, these are fathers of quantum mechanics. So because of the effort of these people, they spent almost 3 decades to understand, to try to find a theory which can describe objects, microscopic objects, like electrons, and answer the questions such as why atoms are stable. And so a simple equation to describe quantum mechanics is called the Schrödinger equation. But instead of going into the details, the mathematical details, I just want to tell you 2 very important principles of quantum mechanics, which is also useful for quantum computation. And one is so-called the superposition principle. So suppose you have an electron with spin. We can view an electron with spin just like you can think of actually every electron. It does not just carry charges. It actually carries spin. What does it mean? Actually, each electron carries a little bit of magnetization. You can think of an electron, besides carrying charges, is actually a very tiny magnet as well. And this magnet, you can have the North Pole up, South Pole down, or South Pole up, North Pole down. So you can think, okay, your electron has this spin, and it's like a tiny magnet. And what is interesting about the superposition principle in the quantum world is that, well, we know that if you have a classical object and it is spin like that, well, and it is spin like that, right? So that's what Newtonian mechanics tells you. It's just, if it's spinning like this, it is in a definite state of this spinning like this, okay? But electron is different. In the quantum world, an electron can be spinning up, denoted by this symbol, this arrow up, and also it can be spinning down at the same time. It's a very weird thing. So it can be spin up and spin down at the same time. Quantum mechanics tells you an electron can be in this room and the room next to us at the same time. It can be at two places at the same time. It can be in two states at the same time. And that's the strange thing about quantum mechanics. And this is called superposition principle. And another very strange thing about quantum mechanics is called entanglement. Quantum entanglement. So, what's quantum entanglement? You have two electrons. Once they are entangled, you can separate them very, very far away. Okay? Very, very far away. So, once you do a measurement on one atom, even though the other one is very, very, very far away, 10 light years away, for example, you immediately change the property of the second particle. This is a very strange thing. You can imagine, I'm operating on the electrons that I have here on my hand, but the other electron is 10 light years away, or okay, maybe closer, on the moon, okay? So when I do something on the electron that I have, immediately you affect the properties of the electron on the moon. This is also a very strange property of quantum mechanics, and that's called quantum entanglement. So,
does it mean that the signal is faster than the?
It's not. It is not. It is not. It cannot be used to transform to convey messages. It cannot do that. But the property of the other electron is changed. Yeah. So it's a very good question. So, and once we understand that, we use this quantum mechanics to understand the property of a single atom. We can imagine, we can use to understand more complicated objects, like the properties of molecules. And then we can, besides molecule, we can combine this, so we understand the atom. For example, you learned this in high school, that the electron binded by a proton has these discrete energy levels. And the energies of the electrons can be written by something like that. Once you understand this, you can combine the electrons, you put them together, you put the atoms together. You understand a single atom, and then you put the atoms together to form a lattice. You can also use quantum mechanics to understand that. Right? When you put the atoms together in a periodic structure, that forms a crystal. So actually, quantum mechanics did not just help us to understand individual atoms, but also molecules, but also materials, like metal, insulator, semiconductors, even superconductors. Okay. So it's a very powerful thing. So in the past, almost 100 years, our understanding, advancement in the understanding of materials, for example, is purely based on quantum mechanics. So, importantly, we can understand materials like semiconductors, like silicon. So, with the understanding of silicon, people can make devices such as transistors, which are the most basic the basic components of modern circuits, electrical circuits. So this is a transistor. So the symbol is made from silicon. You can call the N-type or P-type silicon. You fabricate them together to form a transistor. So this is because we can do that because of the help of quantum mechanics. And each transistor, you can have current you can allow the current to pass from here to here. You can say, okay, that's my one state. And you can do something here to control. You don't allow current to flow from here, from the left to the right, and you can call it a zero state. So a transistor, it's like a switch, but it gives you, it can form a bit, the 0 or 1 state, which is, in one state you allow current to pass from the left to right, a 0 state you don't allow it, for example. And with the transistor, you can combine to form the logic gates. From the logic gates, you can form the circuits. For example, in your cell phone right now, I just looked at it from Wikipedia. So I think if you have the latest iPhone 11, so at the CPU of your iPhone 11 has about, it's very tiny, right? So it has about 8.5 billion transistors in it. 8.5 billion in a single CPU. So that's really, really amazing. So, and this is a guy, a co-inventor, so Shockley. He's one of the person who invented solid-state transistors. And he got a Nobel Prize for that. And he found his company, Shockley Semiconductor Company, in 1956 near Colorado, which is the Silicon Valley, the place where Silicon Valley is. I think the Silicon Valley is the Silicon Valley today. One of the reasons is because of him. So he went back home to try to take care of. That's near, I should say. But Silicon Valley now is actually near his hometown. So after working with at the Bell Lab, he invented the transistor. He decided to go back to his hometown and open a company. And he hired a whole bunch of very bright young people. Here you see the 8 of them. And he got the Nobel Prize, so that's very good. But apparently he's not very good at running a company. So these young people kind of betrayed him. And then they found their own company, and that company is called Intel. So, and then also from Intel, some of them left also found AMD. So all these big tech companies, if you look at the history, they can go back to the understanding of quantum mechanics, understanding of the properties of semiconductors, the invention of transistors, and then using these transistors to make electronic devices. So that's how quantum mechanics in the past almost 100 years really had a huge impact on our world. So, but the transistors, they are getting smaller and smaller. You need to pack more and more transistors together. But that creates a problem. As I told you, in your phone, you have billions of transistors packed in a very small, tiny area. Billions, literally. So that causes problems because when these transistors operate, they generate heat. So you have heating effects. And also, you have those, because these transistors are so tiny, so electrons actually can incidentally tunnel from, when they are so small, electrons can tunnel from one transistor to another. That is called quantum tunneling effect. So nowadays, we are really facing this, we are almost to the limit of how many transistors that we can put into a single piece in a unit area, in a single piece of CPU. We are really almost reaching the limit of how many transistors that we can put there. So, what are the solutions? Well, people are thinking about two. One is, okay, how about I try to find new materials which are more energy efficient. You need less heat, so that maybe I can bypass this heating effect. And but it's still difficult to bypass this tunneling effect. Okay, but maybe you have some levels of improvement. But another is that, well, you can try new ways of doing computation. That's what I'm trying to talk about. So that's the new way is quantum computation. How quantum mechanics can help you. So even though, I want to emphasize, even though the transistors you make is because you know how to make them because of quantum mechanics. But when you are actually doing the calculations, you are not using the principles of some key principles of quantum mechanics to do the calculation. Okay, so which I will explain. So now, just imagine that if we can use the principles of quantum mechanics to do calculations, what can we do? So let's look at a quantum bit. Just suppose we can make that. Just like the electron that we have, our old friend. So this electron, as I mentioned before, because of the principle of superposition, this electron can be at spin up and spin down state at the same time. Okay? So they can be at the spin up and spin down state at the same time. So that means that a quantum qubit can represent both up and down at the same time. Okay, that's fine. If I give you a classical object, a classical magnet, the spin up or spin down of that magnet, okay, well, that gives me one of the states, or the opening or shutting of a transistor, that gives me 1 or 0 state. So now, if you give me a quantum object, a quantum bit, okay, you tell me that, well, I can be in 2 states at the same time. Well, that's great. I can just use 2 transistors to represent that 2 states. Okay, maybe fine. You give me 1 electron. Okay, not a big deal. But you realize that when you have 2 electrons can represent 4 states at the same time, because both electrons can be up, or both of them, the spin can be down, or one of them is up, the other is down, and one of them is down, the other is up. So if you give me 2 electrons, it represents 2 states at the same time. If you give me 10 electrons, or this 10 qubits, that 10 qubits can represent 2 to the power 10 of states at the same time. That's a lot of states. That's about probably 1 million states. That's a lot of states. So, whereas for a classical, if you give me 10 classical bits, at any given time, that 10 bits can only be one of the 2 to the power 10 states. But for 10 quantum bits, it can represent 2 to the power 10 states at the same time, all the states at the same time, at least in principle. So if you give me 50 qubits, 50 qubits. That 50 qubits can represent 2 to the power 50 states at the same time. How large is that? This is billion, trillion, 1,000 trillion states at the same time. 1,000 trillion states at the same time. You just gave me 50 qubits. So that's a lot of states, and classical computers cannot handle this. Okay, so, and more importantly, if I have a classical computer, a classical processor, I put a classical state into it, into classical processor, the output is, well, I have 50 bits, all these 1 and 0 states. You put into your processor, you get maybe some different combination of 1 and 0, but you one state in, one state out, okay? And in the process, your processor changed one state. However, if I have a quantum bit, so I put this 50 bits into my quantum processor, and this quantum bit, because it's a linear combination of 2 to the power 50 states, I just work on this one state, and actually at the same time, I'm working on my quantum processor is able to act on all these 2 to the power 50 states at the same time. Wow, so it sounds really, really powerful, and this is called quantum parallelism. And you ask, well, this is just a picture. Okay, you want to go through this maze, okay? And you start from here. Classically, you just try different paths, one by one, and see, well, how can I go out from this maze? But quantum mechanically, when the particle comes in, it will at the same time explore all the possible paths, all of them at the same time. Okay, so that is the power of quantum mechanics. And it turns out that, well, if you can really make these qubits, and they can help you to do quantum computation, and then they are actually powerful, they can help you to do some things, which can do better than, they can do certain tasks better than classical computers. For example, factorizing very large numbers, and for random data searching. This is quite amazing. Well, if you have more detailed questions, I can answer them later. But this is quite amazing. For example, if you have in your database, you have 1 million objects unsorted. You don't know the sequence of them. You want to find out one object out of 1 million, randomly allocated. So you want to find one data out of 1 million, 1 million data in your database. Classically, you have to search almost 1 million times in order for you to get that data out. But a classical computer allows you to just do it 1,000 times. So this is what is talking about. This is data searching. So if you can make a quantum computer, it can do that for you. And also, as you mentioned, some actually a lot of quantum mechanical processes are very important, and we don't fully understand them. And quantum systems, particularly those involve electrons, which they interact with each other. Those problems are particularly hard. And there are many of those problems, such as if you want to try to understand the chemical reaction between molecules, if you try to understand some materials like high temperature superconductors, these involve very complicated quantum systems, and it's hard to understand. But a quantum computer can help us to simulate those systems and understand them. One of the interesting questions is, for example, if you want to make some fertilizer out of, in the air that we are breathing in, there's a lot of nitrogen. And you want to combine nitrogen with hydrogen so that you can form ammonia or other nitrogen-based fertilizer. And so people can do that. Nowadays, you have industrial processes to do that. But that requires high temperature, high pressure. It takes a lot of energy. Actually, nowadays, because of the farming industry, we actually need a lot of fertilizer. And 1 or 2% of the world's total energy consumption actually goes to making fertilizers like that. But apparently, we are not making it very efficiently. Because bacteria, they don't need high temperature and high pressure to do the same thing. They can do it in a much more energy efficient way. But the industry cannot do that because we don't really understand even a seemingly very simple process like this. Combine nitrogen and hydrogen into ammonia. We don't even fully understand processes like that. So, because these are quantum processes, they're not so easy to figure out. So, if we have a quantum computer, that can help us to understand different chemical processes, and maybe we can find energy efficient ways of, say, making fertilizers. And we can also, as I mentioned, help us to understand complicated materials, such as hydrogen superconductors. So, I talk about for example, this quantum parallel circuit. If you have that, it can help us to do some calculations much faster than classical computers. But why are we not using quantum computers nowadays? We understand the principles already. So the problem is that quantum states are fragile. So, for example, we have this qubit, this state. As I mentioned before, it can be a linear combination. It is superposition of millions and millions of states. And you want to put this state into your processor, and then you try to start manipulating it. So, but the problem is that not just your processor, but the environment is also affecting this quantum state. Your environment can change how this superposition, different states, for example, the weighting of different states can be changed by the environment. So that means that the difficulty is that these quantum states are too fragile. Your environment can easily destroy it, and then you put it in your quantum processor. Even in the process of manipulating it, the environment is also working on it. And your environment will destroy all the useful information you want to get. So this is a major challenge, which is due to the fact that the quantum states are too fragile. You need to protect them. And then the other difficulty is you can create many different qubits. But these different qubits, you need them to talk to each other. In the language that I used previously, you need them to be entangled to each other. So to fully use the power of quantum mechanics, you need to make the qubits individual qubits, very good ones. But at the same time, you need them to talk to each other, and that is actually very difficult. So, and the question is, can we build quantum computers really because of these two major challenges? And you can build, and people are building them. So, but the question is, how could a quantum computer that can be built? And so, as I mentioned in the beginning, there are some companies like Google. They are building quantum computers. And for example, this Google's artificial intelligence lab, and led by a physicist. And this is the machine. And this is the chip, the quantum computing chip that they made. So the material itself is not very fancy, actually. The black one is just a piece of sapphire. Okay, it serves as a platform, or you can think it's like a piece of glass. And then you deposit aluminum. It's not very fancy. Aluminum, aluminum that we have every day for when you drink a soda can. That soda can is made from aluminum. So, but you need to deposit aluminum on top of a piece of glass and make this cross structure, and then you attach some control to it. And what interesting property of aluminum is that actually they can be superconducting at very low temperature, not at room temperature. Okay, they are superconducting at around 1 Kelvin, very low temperature. So, but once they are superconducting, so this cross is represented by the cross here. And an electron can jump into or out of this cross. Okay, an electron can jump into or out of this cross. So, but quantum mechanics tells you the electron can be on the cross, and it can be out of the cross at the same time. If an electron is on the cross, you can say, okay, that's my 1 state. When the electron is not there, you can say, oh, that's my 0 state. So you have this, that 1 and 0 in the presence or absence of the electron, that gives you a quantum qubit. Okay, and then you can put that 9 qubits together to form this quantum computing chip. And actually, you can use that to do some calculations, like simulate. So you can use each cross to stimulate a spin, and then you can simulate how spin. You have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 spins, they interact with each other. You can use 9 crosses to simulate a quantum spin system. Okay. Or you can use them to calculate some energy levels of some molecules, like that. So you can really use that to do some simple calculations. And actually, there are also companies. They started selling quantum computers. So one of these is a so-called D-Wave system, a Canadian company. So, and they sell quantum computers like selling iPhones. They have their first generation D-Wave 1 quantum computer with a 128 qubits. Okay. And then they're making more and more. They put more and more qubits into their chip. And by year 2013, they have this 516 qubits in their quantum computing chip. And by year 2017, they already put 2,000 chips there, qubits there. So and this is the machine that's called D-Wave. And so you see all this big machine. Well, mostly this big box is just to shield the EM wave from the environment. You remember, quantum states are very fragile. You need to shield them from the environment. And then these big pieces, well, part of it is to control your qubits, but another part, one of the most important parts is actually to put down to a very low temperature. Actually, your quantum computing chip itself is actually very tiny. It's actually very tiny. And this is a D-Wave chip. So on each chip you pack many of them together. Each of them you have 7 qubits. But as I talk about, It doesn't mean that D-Wave really makes very powerful computers, because you can create many qubits. But as I mentioned, in order to fully utilize the power of quantum mechanics, you really need to make sure that the qubits themselves are talking to each other, or they are entangled to each other. But this is very hard to do, and it's not believed that the qubits made by the company are fully entangled. Okay, and it is probably not. And who are buying them? There are lots of companies buying them. So if you know who they are, so this is Lockheed Martin doing making lots of weapons, unfortunately. And you have Google and NASA. You have this Los Alamos National Lab. They buy quantum computers from this D-Wave company. This is a laboratory which made the first atomic bomb in the world. And you also have Volkswagen, the car company, probably trying to use a quantum computer to solve some optimization problems. So, and you can ask, okay, how much are they cost? Each of them costs $50 million US, okay, from the D-Wave company. So IBM is also making quantum computers. And Intel, as I mentioned, also making quantum computers. And so what are the remaining challenges? Oh, people are doing that. So what are the remaining challenges? The main challenges is the qubit coherence time is very short. Okay, maybe in hundreds of nanoseconds. So very quickly, because of the effect of the environment, the effect of the environment can quickly destroy the information you have for your qubit. Okay, that time is very short. It's in the order of hundreds of nanoseconds. Very short time, and then the information is gone. So, and that means that you need to do operations within that very short period of time in order for you to do some meaningful calculations. And also, it's very hard to entangle this qubits together. So you hear a lot of this. You are hearing a lot of the news about. Nowadays, a lot of news. Oh, IBM is making this 20 qubit quantum computer. Oh, Intel is making this a 50 qubit. Google is making this a 70 qubit. You heard a lot of words like that. What does it really mean? In principle, if you have a fully entangled 50 qubits quantum computer, if these 50 qubits, they are fully entangled and you can make use of them, this is already very powerful. Because, as we talked about previously, if you have 50 qubits, this 50 qubits can represent 2 to the power 50 states at the same time. This is already the limit of any classical computers that can handle. It's beyond any classical computers can handle. So these companies, they are trying to build computers, quantum computers, which are more powerful than classical computers. So, and well, they are trying, but it's not so sure that how successful they are at this point. I mean, in doing meaningful calculations. And that's another company which I did not mention, which is Microsoft. Microsoft have they have a different plan of making qubits. Instead of using electrons or pairs of electrons, like so-called Cooper pairs, so they use a different particles called Majorana fermion. So it's just that you can think of each Majorana is a 1/2 of a fermion, or 1/2 of an electron. Not completely, but you can imagine that. So you can put this two Majorana fermion together, and then another Majorana, 2 Majoranas together. These 2 Majorana, they can form a state, and that state can be occupied or empty. So two of them, two marijuana, can form a qubit. And if you have many, many pairs of marijuana, that give you many pairs of qubits. And you can entangle them by moving this marijuana fermions around. So, and then what you get is the quantum state, which is fully entangled. So, and this is a very interesting scheme. Actually, this is the marijuana particles. This is a subject that I studied in the past decade. So you can find these marijuana particles, for example, if you have a nanowire, you put a superconductor next to it, and also you need to apply magnetic field. But in any case, you can find these marijuana fermions in some special types of superconductors. And this gentleman here, Neil Calvin-Hoven, he visited us a few times in Hong Kong here. And this gentleman is one of the leading instrumentalists for Microsoft for searching marijuana fermions. And I'm a theorist, so my job is to predict if you have a marijuana fermion, what you will see. How can you tell? You do some experiments. How can you tell if the marijuana fermion is there or not? So many years ago, so we had some theoretical prediction. We tell the experimentalists that, oh, okay, if you have marijuana here, and then you try to inject some electrons from your lead through the marijuana to the superconductor, oh, you will see some peak in the middle, like that. So we predicted something like that. And it was actually later verified by the Delft group. So for example, we predicted experimentally you should have some peak in the signature when you do the experiment. And that peak, we predicted how high that peak is in the unit of 2e squared over h. It's quantized at precise that value if you have marijuana fermion. So we predicted that in a theoretical paper. That is back in 2009. And actually that prediction was verified recently, last year, by Calvin-Hoven's group, by this gentleman's experimental group. So, excuse me. So here's the summary. So you see that many big companies, they are doing it. So at the beginning, I talked about many of the big companies like AT&T, like General Electric, like IBM. So you see that these are the big technological companies of their time, 100 years ago. So and they still are today. So if you have the technology, and then you can make useful things, and you can increase productivity. You can help people, or you can create job opportunities, right? So that's why when people realize that, oh, you have the prospect of quantum computation, maybe you can make much, much faster computers than classical computers. And you can use this quantum computer to understand chemical processes. It can help you to have a better understanding of drugs. It helps you to have a better understanding of materials like hydrogen superconductors. So, and when you have big potential applications like that, so these big companies, and they want to study, they want to invest in it, and they want to see how they can make use of it. And they want to be the leaders in that area. So that's why quantum computers are being built all over the world right now. Alibaba also, Tencent also has recently. These are also Chinese-made technological companies. They are also interested in this quantum computation. So these quantum computers are being built around the world, And that's why we are here today, that we need to prepare our young people for the opportunities and the challenges to come. At least you know what is there in that field, what's really happening, right? What is quantum computation, how we can use them. And maybe one day, okay, if you learn quantum mechanics well enough, you can find a job there. Okay, this is the lecture. Thank you very much.